Okay, we have here today another integral from the MIT Integration Bee 2024 regular season number 9. We have the integral from 0 to infinity, x ln x over x to the fourth plus 1 dx. Okay, this was actually pretty tricky. The first problem I see here, it's just hard to have natural log here with all this other stuff. I did try on paper doing this with integration by parts, but it seemed like kind of a mess. So what I want to do instead is I just want to make a u substitution for ln x. And let's see if we can get some simplification this way. So we'll just say, we'll set u equal to ln x. And I think what I'll do is solve for x right now just by rearranging this with the properties of the log. With properties of log, I can write this as x equal to e to the u. And then I'll go ahead and take my derivative. So for dx, we're gonna have this is just gonna become e to the u du. So first updating infinity, ln of infinity is still gonna be going to infinity. Then for 0, ln of 0, our lower bound is going to be minus infinity. Then for x, this is going to be e to the u, and of course ln x is just u. Now for our dx, this is going to be, I'll write this as eu. Then for x to the fourth, we take e to the u to the fourth, and we can write this as e to the 4u plus 1. And now of course we could multiply e to the u times e to the u, but actually I'm just going to clean that up, so I'm not going to worry about it. But what I want to do in order to rearrange this, I'm going to multiply by 1, but I'll just multiply by e minus 2u over e minus 2u. So when I do that, that's going to cancel out with this and this here. And then we'll just rewrite this and see what we have. So then the numerator is just going to become u du. E to the minus 2u times e to the 4u, this is going to be e 2u, plus e minus 2u times 1 gives me e to the minus 2u here. And then this is kind of interesting because what we have here, this is actually an odd function. Just notice in the denominator is like 2 cos 2u, or however you want to do it. This denominator is even, and then the numerator is going to be odd, so this whole thing's odd. And you may think the bounds are symmetric, so we can just put down the answer as 0. But the trouble is, to use this principle, we actually need the bounds to be finite, so we're not so fast, we can't really say that this is 0. But still, we can fix this pretty quick with another substitution. So what I'm going to do for this, I'm going to make another substitution just saying, we'll set t equal to minus u. Then, of course, u is going to be the same thing as minus t. I can take a derivative, and our du is going to be minus dt. So then we'll go ahead and substitute this. So putting in infinity, this is just going to, everything we're just reversing the sign. So this bottom, so our lower bound is going to become infinity. The u here is going to be a minus t. Du is going to be minus dt. We're going to have e minus 2t plus e plus 2t. But then I'll take this minus sign out front and use it to swap my bounds. So we'll swap this, and now we're back to having the same bounds we have here. I can take this minus sign and bring it out front of the integral. Then one last thing, let's do a variable change. I'm going to change it back to u because I want to work with this copy that I'm going to label I right here. So when I come down here and we rewrite this, we're going to have our minus out front, infinity minus infinity. This is going to become u du. I'm going to reorder this and write this as e2u plus e minus 2u. But then the thing to notice is what we have here. This is actually the exact same thing what we have here. So this is a copy of I. So we end up with this simple equation, I equals minus I. We can add an I on both sides. We get 2I equal to 0, or just I equal to 0. So there you have it. Interesting integral from MIT 2024. Thanks everyone for watching. Have a good day.